Okay.
Okay, so today we have Simon Murphy from University of Sydney. He's a recent ARC Future Fellow, and he's going to be talking about asteroseismology from what I see here. Yeah, so without further ado, please, you may begin.
Thanks very much. Yes, I am an ARC Future Fellow. Actually, my Future Fellowship starts today, which is kind of cool. I'm moving to the University of Southern Queensland. The work that I'm presenting to you today was done at the University of Sydney, and it's not just my own work. This is work that I've done with Tim Bedding, Tim White, who are both at USyd, Meredith Joyce, who was at ANU and has recently moved to STSCI, and Dan Huber, who's at the University of Hawaii. He's also a Future Fellow. He'll be going to USyd towards the end of this year, and many other people too, and I'll mention those contributions as I get to them. But this work is all very recent stuff, basically from the last year or so. So forgive me if it doesn't seem too polished, but hopefully I'll be able to convey that to you and convince you this is all very exciting stuff. So precise asteroseismic ages from young pulsating stars. Let's start with a bit of an overview of what I mean by young stars. Here's a map of the Scuti star forming region. And in this map, age is encoded with color. So the youngest stars are in blue. That stretches down to about 5 megayears. And the oldest stars here are only about 27 megayears in the dark red. So objectively, these are very young stars. This map was determined using about 200 stars, primarily through the lithium depletion boundary method. And you get this nice colorful age map. One of the things you'll notice about this age map is there's a very clear age gradient that basically cuts across the graph, right? So in the upper left, it's the youngest stars, and the lower right, the oldest stars. And superimposed on that age gradient is what we call age dispersion. So you get older stars in little pockets. So like there's a little pocket here where the stars are a bit older than would otherwise be implied by the general gradient. So let's say you want to determine the age of a star in this association based purely on its position on the sky. And so we might look at HD 139614, which is a star that I'm going to talk about a lot today. And from this map, you would infer an age of about 14 megayears. There's about 1 megayear of sort of random uncertainty. And there's about 3 megayears of systematic uncertainty embedded in this map in terms of the way that ages are determined and how reliable our ages are when they come from the lithium depletion method and stellar models in general. We also modeled this star with asteroseismology, and then we get an age of 10.75 megayears, so a little bit younger. But we also get a pretty small uncertainty that comes out about 7% age uncertainty for this star. And that young age means that this star is on the pre-main sequence. And we'll talk a little bit more about why that's important later on. So how do we determine stellar ages? Normally what we're doing is we're mapping some set of observables. So that could be parallaxes, velocities, you could have some spectroscopy and so on. We're trying to map them to some stellar parameters: mass, metallicity, age. Sometimes we include rotation. And the most commonly used method to do this involves stellar isochrones. And those are great most of the time, but they're not always great. If you're trying to determine the main sequence turn-off age of a cluster with an age over a gigayear, they're totally fine. But you have to be aware that isochrones of different metallicity will overlap. Pre-main sequence isochrones will overlap with main sequence ones. And the isochrone ages are very dependent on those observables that you're putting in. So your parallaxes, your temperatures, and so on. I think it's worth taking a look at how strong that dependence can be. So imagine you've got a star with a planet-forming disk. Disk evolution is rapid. It occurs on timescales of 3 to 5 megayears, and so precise ages really matter. If you want to pin down what's happening in the evolution of a planet-forming disk, you really need a precise age. But if you've got some obscuration by that disk, or the star's just generally in a dusty environment because it's in a young cluster or a young association, you might end up with the wrong luminosity because you're going to have a high uncertainty on your extinction. Or if the metallicity that you measure from that planet-forming disk has been modified by the planets that orbit within it, you might end up with the wrong metallicity. On top of this, early type stars tend to rotate very rapidly. We're talking 200 kilometer per second rotation rates a lot of the time. And that can give you the wrong temperature, it can give you the wrong luminosity, there's extra mixing involved, and so on. Now, there are also different ways that you can measure ages. You can use empirical age indicators like gyrochronology or the lithium depletion boundary, but those only really work for sun-like stars. And so your best bet really is to try and use isochrones on a whole bunch of stars in the same association and come up with a sort of, excuse me, come up with a sort of ensemble age that represents the association as a whole. So not every method is applicable to all types of stars. Like I say, the lithium depletion method is only going to be for cooler stars in general. I want to highlight for you how difficult ages can be, and I want to take a look at the Pleiades as a specific example of this. For the Pleiades, we get a wide range of isochrone ages, and we get a strong dependence on the treatment of rotation. So from non-rotating isochrones, we infer an age of about 100 megayears, but when we start to include rotation, we find a range of ages that fit pretty well, between about 100 and 160 megayears. That's a pretty large uncertainty, right? We're talking in excess of 30% uncertainty a lot of the time there. Now, there are two main effects of rotation. One of them is that the star becomes oblate. So you get gravity darkening, the temperature and the luminosity depend on the observing angle. So if you're observing the star from a pole-on angle, you'll see it being a bit brighter, so a higher luminosity. And if you observe from the equator, the star will appear a bit cooler. This deformation goes as omega squared. So for the slowly rotating stars, it's really not a problem. But if your star rotates at 200 kilometers per second, you've got a pretty big problem. You've got a lot of gravity darkening. And the effect of this is that the star will become displaced with respect to non-rotating isochrones because it will be brighter or it'll be cooler or some combination of the two. The second main effect of rotation is that you get extra mixing of material. So you get fresh hydrogen that gets mixed into the stellar core. That will extend the main sequence lifetime. And so if you're trying to do something like look at the main sequence turn-off age, you'd better be accounting for rotation. Otherwise, you'll be getting the ages wrong. For the Pleiades, we also see overly precise lithium depletion ages. We see a strong dependence on sample selection and on the model physics. So with the lithium depletion boundary method, we get an age of about 130 megayears with a 20 megayear uncertainty. That seems pretty reasonable. It's consistent with the ages we get with rotating isochrones. If we apply the lithium depletion boundary method just to the brown dwarfs that we see in the Pleiades, then we get a considerably younger age and a very small uncertainty. You could say an unrealistically small uncertainty. And then if you account for magnetism in your stellar models and you look again at the brown dwarfs, and the age that you get is younger still. And so you start to see that there is substantial systematic uncertainty in the way that we are determining stellar ages. And that was investigated in a series of 3 papers by Garrett and Pinsonneau. They looked at, for instance, the effect of differential rotation and how you treat that. The way that you treat star spots also matters, and the ages at which star spots either become developed or become detectable depending on how much of the star you can see in its early evolution. And their conclusion was that you get systematic uncertainties of 10 to 20% for 100 megayear old clusters. And on the pre-main sequence, we don't even really have a good estimate of what the uncertainties are or should be. The age map that I showed you earlier, that had lithium depletion boundary uncertainties of 25% embedded within it. So when I quoted that systematic uncertainty, that included a systematic uncertainty for that specific method. So most ages for the Pleiades come out in the range of 160 to about 100 to 160 megayears. There's only been one asteroseismic study so far, by which I mean 2 sort of last year. And that was from 2006. And they used a hard age prior of 70 to 100 megayears. And unfortunately, that means they sort of, they might have set that prior a bit too young. And so the conclusions drawn might not be sort of sound based on what we now know of the cluster age. And then don't forget that age uncertainty that exists for young open clusters is the minimum uncertainty that you can expect elsewhere on the HR diagram, because this is how stellar ages are calibrated. So if we can't get good ages for young clusters, we're kind of in trouble. My message to you today is that asteroseismology can provide precise stellar ages. There are only weak dependencies on the typical observables. So we might use, for instance, the stellar temperature as a ballpark estimate, but things like dust obscuration are not a problem. We don't need precise luminosities as a constraint. This also works for single stars, so you don't need an ensemble. And you can both measure and properly account for rotation. And that's not to say that rotation isn't a problem. I really assure you that it is. It's a real pain. But we can measure it and we can account for it. The model physics is always going to be a problem, but we can improve it. So if you get pulsating stars and eclipsing binaries, for instance, where you get well-measured stellar radii, then we can start to improve the model physics. And that might include things like convective overshoot or diffusion near the core and things that might extend the lifetime of the star. That kind of physics that's otherwise hard to observe. So we can improve cluster age benchmarks and therefore improve the whole age scale by getting precise asteroseismic ages of young stars. And that's the project aim of my future fellowship, really sort of focusing on those young stars. So I want to convince you of this using a case study, and that's HD 139614 that I mentioned earlier. So with this star, I aim to answer the question of why we need precise ages. This star has a warped planet-forming disk. That disk has ring structures and cavities within it, and that's why we think this disk is currently forming planets. So what you're seeing on the left is a polarized scattered light image. Within that image, there are rings near the star. There are arcs that you can see further out. And the fact that the image is sort of bright on the upper right and faint on the lower left is an indication that the disk is warped. And the inner ring is sort of obscuring a lot of the light from the star from reaching the outer ring, the outer arcs. So I'm talking about this region down here. The light is basically blocked by this inner ring. And then if we look at the model of this disk on the right-hand side, you were looking at a radially integrated optical depth there, and you see a pretty large gap at a radius of a few AU, and that is something that is believed to be an indication of a planet that is embedded within the disk and is sweeping up a lot of that material. So we're going to see that asteroseismology can offer very precise ages for this star and this disk. So before we go further, I should probably explain a bit on how asteroseismology works. A star will oscillate at its natural frequencies, and different oscillation modes will penetrate to different depths throughout the star based on both their degree and their radial order. So the degree is the number of nodes that exist on the stellar surface, and the radial order is the number of nodes that exist throughout the star. These lines here are examples of radial nodes, and you can see these modes bouncing around on the surface, and that's where the modes have nodes at the surface. So the travel time, or the period of these modes, depends on the internal density profile of the star, as well as the star's size and its composition. So those pulsation periods, or the reciprocal of them, which is the pulsation frequencies, these are the fundamental data of asteroseismology. And we can use those to probe the stellar quantities, particularly that density profile throughout the star. In order to do that, we need to be able to identify the pulsation modes. We need to be able to assign values of N and L to each of the observed pulsation frequencies. So here's how that works for stars like the Sun. This particular star is 16 Sig A. It was observed by the Kepler Space Telescope. And what you're looking at is a Fourier transform of the stellar light curve. The pulsation modes are found in this sort of almost Gaussian-like pulsation envelope. And then within that envelope, you see basically a comb-like pattern of pulsation frequencies, right? And that alternates between L equals 0 modes, the radial modes, then you get a dipole mode, and then a radial mode again, and then a dipole mode again. And you will occasionally get L equals 2 and L equals 3 modes as well. we notice, for instance, one thing, that the L equals 0 and L equals 2 modes are always found close together. And then the L equals 1 modes are pretty much found on their own about halfway between consecutive modes of L equals 0. So we call that spacing between consecutive modes delta nu. That's the large frequency spacing. And that scales with the square root of the mean stellar density. So if you can measure delta nu, you can basically measure the stellar density. But today, we're not going to be talking about solar-like oscillators. We're going to be talking about delta Scuti stars, which are classical pulsators about 1.5 to 2 times as massive as the sun. And this is where they are located on an HR diagram. Sorry, you'll have to forgive my cursor. There's a bit of an offset between where I'm pointing on my screen and where you can see it on your screen. So I'm trying to use an iPad to like align that up. I don't know why that's happening. But yeah, so the delta Scuti stars are here. They're about twice as massive as the sun. And they are at the base of the classical instability strip that also includes Cepheid variables and Haralari stars. So what I'm showing there in purple is an evolutionary track of a typical 2 solar mass delta Scuti star. It's important to note that historically we've kind of failed with delta Scuti stars. We've seen that stars that lie near each other on the HR diagram have a seemingly random subset of excited modes. So I've got 4 examples of delta Scuti stars shown on the right-hand side here, showing their Fourier transforms. These are 4 that are located very close to each other, but their Fourier transforms all look very different from each other, and there's no real discernible pattern there. You certainly can't look at those and pick a sort of a definitive value for delta nu. And so without regular patterns in the pulsation modes, the mode ID becomes intractable, and without that mode ID, we can't do asteroseismology. So if they're so difficult, why am I mentioning them? Why should we be interested in them? Well, in 2020, we had a breakthrough. This was a paper that was led by Tim Betting, published in Nature, where we discovered very regular patterns of pulsation modes in these young delta Scuti stars for the first time. So here on the right-hand side again is a bunch of Fourier transforms. This time you can see that regular comb-like pattern, and you can see that from one Fourier transform to the next, the peaks sort of almost line up. They line up well enough that you can sort of track the same peak between different stars, okay? So that asteroseismic large spacing, delta nu, has become a new observable for delta Scuti stars, and it's giving us a handle on the mode ID. So I'm going to return now to our case study from before, HD 139614, and this is a delta Scuti star. In the top panel, you're seeing its light curve from TESS. So TESS measured the brightness of this star, as well as hundreds of thousands of other stars, every 2 minutes for a period of 1 month. And the bottom panel there is the Fourier transform of that TESS light curve. Now, just ignore the circles and the triangles for now. What I want to convince you of is that particularly on the right-hand side, we can see regular patterns between the modes. So if you divide the Fourier transform into regular segments of size delta nu, 6.83 cycles per day in this case, and you draw those as dashed lines, you'll see you've got a little triangle just to the right of each of those dashed lines, okay? In every single window, you've got these triangles. So these modes have this regular spacing, and that spacing is delta nu. Now, we know that 6.83 cycles per day is quite large, and we know that delta nu goes as the square root of the mean stellar density. And so this star is very dense, and from this we know that it's very young. The reason we know 6.83 is quite large is because we have this sample of 60 or so of these high-frequency delta Scuti stars from the Nature paper against which to compare. So when we analyze these stars, we use a tool that we call the shell diagram, and I'll give you a bit of a run-through of how this works. You take the Fourier transform of the star, divide it up into segments of size delta nu, then stack those segments vertically. You encode the amplitude information with color, and that gives you the shell diagram. Now, I know that was a bit quick, and this is important, so I'll go through it again. You take the Fourier transform, you divide it up into equal segments of size delta nu, and then you stack them vertically with the highest frequencies at the top. You encode that amplitude information with color, and that gives you the shell diagram. So here's what the shell diagram looks like for HD 139614. All of those triangles that I mentioned before, they're on the left-hand side of each window. If you imagine the frequency space between two dashed lines to be a window, the triangles are on the left-hand side. And so in the Echelle diagram, the triangles all fall down the left-hand side of the diagram. The radial modes sort of curve down through the center. So if I just sort of overlay some shaded regions here, this is the pattern that we see not only in this star, but in all of these high frequency delta Scuti stars that we look at. And we know this by comparing with models that the L=1 modes fall on the left-hand side of the Echelle diagram. The L=0 modes curve down the center. This is a new development for this type of star. Mode identification was previously intractable, but using this knowledge, we can identify 7 dipole modes and 4 radial modes in this particular star. And that allows us to do some asteroseismic modeling. When we do that, we have to be careful with our mode ID. So what we're trying to do is we're trying to do a chi-squared minimization between the observed frequencies and the model frequencies. But it's not necessarily the case that the strongest peaks are the ones that belong in the patterns. So if I go down to where there's arrows pointing on this particular row of the diagram, you can see we've identified a peak that's to the left of the strong peak, right? So the strong peak is not necessarily the one that fits in the pattern. That's really important. And it's essentially a source of uncertainty in the modeling. So what we do is we create many different mode ID scenarios. So in one scenario, we might pick the strong mode, and in another scenario, we might pick the mode that gives the straightest ridge, and so on. For this star, we use 10 different mode ID scenarios, and then we take the one that has the lowest chi-squared out of all of them. The way we do this is with a bit of grid exploration. So we calculate a model grid. We use MESA for the stellar models, and we use Gaia for the pulsation calculations. And here's a set of evolutionary tracks that are computed with MESA. These are spaced by 0.02 solar masses, and these are pre-main sequence tracks. So the star is coming down from the right-hand side, and then sort of winds its way down to the zero-age main sequence, where these calculations are terminated. The track that's in orange, I've also shown the main sequence evolution for this. And so you can see that the main sequence evolution of one track will overlap with the pre-main sequence of another track. And this is why with isochrones, you have that problem. If you don't know a star is on the pre-main sequence, it becomes pretty difficult to fit with isochrones. Another thing that we can do if we have the data available is use a starting point, which would be your classical error box. So your sort of, in this case, 1 sigma temperature and luminosity measurements. We tend to start with a roughly solar metallicity because that makes life a bit easier. We have to start somewhere, but that's not like a final determination, and it's not really used as a prior, it's just a starting point. And in this case, for this particular star, because it had a planet-forming disk, we used a hard prior on the age, and we said the star must be younger than 30 mega years. Again, you have to start somewhere, and this also massively cuts down the amount of evolutionary modeling that we have to do. So we end up with a grid, and the grid looks a little bit like this. What I'm showing is a grid in terms of mass and metal mass fraction Z. And each point in this diagram actually represents an entire stack of models. It's an entire evolutionary track, right? So for any given point, let's just take this little green point that's isolated down here. It has some value of mass and metal mass fraction, but it also represents all of the ages from, you know, like a fraction of a mega year up to hundreds of mega years, although we did terminate at 30 mega years in the end. And what's shown is the lowest chi-squared out of every single point in that stack. And so what you see is the points where a chi-squared was calculated are the points that pass through that classical error box at some point in their first 30 mega years of evolution. And then the lowest chi-squared points can be found in a global minimum over here. And you can see that we've explored the parameter space around it to make sure that that is a global minimum and not just a local minimum. And that's why I say it doesn't really matter where you start with the metallicity. We did start with a roughly solar metallicity, which would be about here. And then we sort of migrate down towards the best fitting solution, which is somewhere in this parameter space here at slightly subsolar metallicity. One thing we do is we make a corner plot. Hopefully everybody's familiar with corner plots. So you're basically just making a scatter plot for every parameter against every other parameter. And so in gray here, we've got every single point that was evaluated, which was 10 to the 5 models. In color, I'm showing all of the models that had a chi-squared less than 1. And in red is the convex hull of those points that also agrees with the known temperature and luminosity. Okay. When we do this, we get about a 1% precision on the mass, 10% on the metallicity, and 7% precision on the stellar age. We found no dependence on the mixing length alpha, which is nice because that means going forward we have one less parameter that we have to compute models for. It saves us a lot of time. So that was 100,000 models that we evaluated. Now, how do we get such precise values? How do we get sub 10% precision on the age? Well, on the left are the evolutionary tracks that I showed before. And on the right, what I'm showing is the evolution of delta nu, the large spacing, as a function of age. And what you can see is that there is a mass dependence to this graph, right? So the more massive stars are going to evolve a little bit more quickly, so they're going to reach their highest values of delta nu a little bit earlier, and that separates the tracks. And that really allows us to hone in on the correct mass and therefore get a better precision on the age, because we don't quite have the degeneracies that we might have in other parts of the HR diagram. So I quoted an age precision of plus or minus 0.77 megayears, which is about 7%. What I'm showing in this shell diagram is the effects of plus or minus 0.2 megayears on the frequencies, right? So in purple, I'm showing a model that's younger than our best fitting model. And in orange, I'm showing a model that's older than our best fitting model by about 0.2 megayears, which is only 1/3 of the quoted age uncertainty. And you can see it's very easy to distinguish between our best fitting model, so this green one, and the fit that you get for the younger model and the older model, respectively. And since that frequency difference is so large, you can see all the way down this dipole ridge, you might ask, well, in that case, why have you quoted such a large age uncertainty if it's quite clear that the precision that's possible with these models is much better than that? And the answer is that age is not the only parameter that we have to marginalize over, right? So you also have to account for the fact that we don't know the stellar mass with infinite precision. We don't know the metallicity to infinite precision. And so when you fold all the uncertainties together, the age uncertainty that we end up with is a bit larger. One thing that is apparent, though, is that the highest frequencies are the ones that confer the greatest sensitivity. Okay, that's quite important. I did have an animation here of the evolution of a 1.7 solar mass star, but I think I might just skip that one in the interest of time and point out that this method, this way of determining the age of stars, works very well for many young stars and associations. It's not just that one star. Here's a few more that I've been working on. And you can see we get pretty good matches between the observations and the models. Alrighty, back to the Pleiades for a little while. One thing I was particularly interested in was trying to get a good asteroseismic age for the Pleiades with this method and comparing it to the ages that we get in the literature. This is a work that's ongoing. So far, I have investigated it using non-rotating models, and in the future, this will be extended to some rotating models. So there are three stars that we're going to look at principally today, and these are the three slowest rotators that have high cadence observations from the K2 spacecraft. Now, we made custom light curves for these stars. In fact, Tim White made these light curves, and I'll show you why the custom light curves are necessary. Here's a full frame image from K2 for 5 of the stars that have high cadence observations, short cadence observations. And if we look at, say, V647 Tau, there's a couple of bright stars nearby. And if you look at its standard aperture and its sort of target pixel file, there's this very bright saturated column streaking all the way down the center. So if you use a standard aperture, you end up incorporating part of that flux from those saturated pixels, and your light curve is a complete mess, okay? So you have to do something to account for that. And the same with V1228 tau, that star is bright enough to saturate the detector, and so you have to do some clever stuff in order to capture all of the flux. So I'll give you a bit of a before and after of what these stars look like. There's V647 tau on the far left. You're seeing changes in flux of about 20%. But after Tim White did his clever light curve creation, you end up with just the pulsational variability, which are changes of less than 1%. That's the kind of scale of the correction that we're looking at here. So it's kind of easy to see why these data didn't receive much attention before. The light curves were a bit of a pain, but I think Tim did a really good job with them. So here are shell diagrams, and I hope you can see that there are some clear ridges in this diagram. So if we look at V624 tau in the center, for instance, you've got a ridge down the left-hand side, which we might expect to be the dipole modes. And we've got a clear ridge coming down the center that then curves to the right, gets a bit messier lower down, but you can see that we should be able to identify some radial modes there too. So here are those mode identifications. I'm also using brown crosses to point out modes that we didn't successfully identify. But for V647 tau, you can see we've got a pretty clear radial ridge down the center. And then for the other two stars, we've got both dipole modes and radial modes. Now, V647 tau, you might wonder why we don't have a dipole ridge labeled. The reason is I think that these modes are rotationally split modes. So the frequencies of any mode with radial order n, degree L, and azimuthal order m is equal to the frequency of basically the non-rotating component, the m equals 0 component. And then you add a term that depends on omega, the rotation rate of the star. And what I think is happening is that those modes are shifted by rotation because they don't fall, they're not in agreement with any of our non-rotating models. They sit slightly offset at higher frequency. And so I think those are the prograde modes. But obviously this is a hypothesis that's yet to be proven because I'm not using rotating models for these stars. So I did some modeling with MESA and with Jaya. Again, non-rotating models. For the metallicity, I used the published metallicity from I believe it was G dwarfs from Dave Soderblom's paper to 2009. And that corresponds to metal mass fractions that you can see there in the upper left. I used basically a helium enrichment law that says if you change the metallicity, then you have to change the helium abundance by 1.4 times that change. And the starting helium abundance is 0.28. Then the mass range was between 1.7 and 1.9 solar masses, and the age range was between 50 and 180 megayears. That's a very broad range, but I didn't want a hard prior to basically influence the results, and so that was the age range that I chose. Remember that the published values are between about 100 and 160 megayears. So there are all of the evolutionary tracks that were used to try and model these stars, and here are the results. The model frequencies here are plotted as open symbols. And I think that's a pretty good match, even if I say so myself. So you get good matches, but the best fitting model is always the oldest and the most massive and the most metal rich that is available for that star, right? So what that translates to is that we're always finding the least dense model in the grid that's matching these observations. And the reason that we consistently find the least dense model is that these models are non-rotating. Obviously, in real life, these stars are rotating. Some of them have velocities around 100 kilometers per second. And so there is going to be some distortion due to that rotation. The distortion is going to make the star oblate and therefore less dense. And that's basically what the models are trying to replicate, but they can't because the models are not rotating. So that's essentially a problem for future work, is to reconcile that lack of rotation in the models with the observations that we have. But rotation also offers another opportunity. We can directly measure that rotation with asteroseismology. I mentioned the rotational splitting that we see and the frequency shift that we see for rotating modes and prograde modes. Rotating models and prograde modes. So from that asteroseismic frequency splitting, you get an internal rotation rate, omega, and omega is basically 2 pi divided by the rotation period. From spectroscopy, we measure V sin I, that's the surface rotation rate, but it's convolved with the unknown inclination angle. And your best fitting stellar model will give you a stellar radius. And then you can use some first year astronomy algebra here, and you can do your speed equals distance over time, and you can rearrange your equation for the inclination. So basically you can work out the inclination rate of the star based on your observed V sin I and your observed omega, your frequency splitting. Then if the star has a disk, like our earlier case study, HD 139614, you can measure the disk inclination either from your scattered light images or the models or whatever it is that you're doing in your analysis. And you can compare that inclination to the stellar rotational inclination that we worked out over here. And then what you've just measured is a spin orbit alignment or misalignment during that planet formation process. And that's an observation that we can't make in any other way. The disks are optically thick, so we don't get clear planetary transits with which to do, Ross to McLaughlin type observations. So this is the only way that we're able to do this at present. And then if you do this for half a dozen stars, you've basically got yourself a science case for an ARC discovery project. So I guess we all know what I'm going to be doing over the next few weeks. Incidentally, if this is your jam, if you're working on inclinations or spin orbit misalignments for young planets, definitely get in touch. I would love to have some collaborators on this project. All right, so that was sort of part 1 of the talk, and I want to do a part 2 now, which is the population statistics of these young pulsating stars. And this section of the talk is based, yes?
Sorry, before you go into part 2, is it okay to ask a quick question?
Or yeah, go for it.
At the end?
Yeah, please.
So I think this is fascinating. I was wondering if how sensitive you think you are to overall model systematics, right? So you still have this issue that ultimately you are trusting a MESA model of stellar evolution. And of course you mentioned, okay, not including effective rotation can significantly bias you, but there are other free knobs within MESA where we don't, there's lots of bits of stellar evolution, semi-convection, for example, and things like that we don't, fully understand. We don't know what the right expressions are. And I was curious whether you have some estimate for, I don't know if you've tried playing with those knobs, for example, within reason and seeing how different the stellar tracks would be, and therefore how different the fits would be, and if those systematics are comparable to the measurement uncertainties you're currently quoting, or if they're much smaller, or what the case may be.
Yeah, that's a great question. In the paper on HD 139614, we did try and quote uncertainties that incorporated some of the systematic uncertainty. It wasn't a complete analysis of all the systematic uncertainties that we have in the modeling, because as you say, there are lots of different things that you can mess around with and compare your results. So we did do some things like, whether or not you include deuterium burning, and like I said, we did use the mixing. We did change the mixing length, and we found that that was not so important for these young stars. One thing to keep in mind is because the stars are so young and have recently been fully convective, we don't have a lot of the uncertainties that you would normally get with things like diffusive mixing. You don't have much stratification happening within the stars at all. So we did discuss a few of these things. We haven't done a complete analysis yet. One of the things that we looked at that we didn't really write about was in MESA, you can change various sort of mesh coefficients. So how many different zones do you divide the star into? How regularly do you output all of your parameters, like your age and so on? So how frequently do you calculate models throughout the evolution? We played around with a lot of that stuff, and we just chose parameters that we we decided were sensitive enough, but we didn't really talk about that in a lot of detail. I would like to do a very thorough study of all of the systematic uncertainties involved in this modeling. And yeah, sometime in the next 4 years, I guess, is when I'll get around to that. But yeah, the uncertainties we quoted in the paper, we did intend to account for known systematic uncertainties that existed within the models. Does that make sense?
It does. Thank you very much.
No worries. Okay, so part 2, population statistics. This is based on undergraduate work by William Young. He did 2 semesters of undergraduate project work with me on this. So, you know, major credit goes to him on this. He did a fantastic job. There's a lot of science packed in here in this one diagram, actually. But first, I'll explain how we got here. So if we want to analyze a large sample of these stars, we're going to need to automate ridge detection in the Echelle diagrams, right? Or at least automate a method of determining the large spacing. There are tens of thousands of stars observed by TESS, and it's just too time consuming to do mode identification for every single one of them by hand. So Will's first task was to try and automate this, this mode ID, basically. So one thing you can do is you can take the autocorrelation of the Fourier transform. That's what we did in the Nature paper. It's simple, it's proven, it's robust, but can we do better? What Will came up with was a line scanning algorithm. So this finds suitable lines when the gradient is basically vertical and looks for lines where the scatter about that line is small, and it prefers sort of long lines, so long sets of modes all in a vertical line. And so he came up with a performance metric, performance value, which is the residual sum of squares divided by the gradient multiplied by the line length squared. That's what Will came up with, and it works pretty well. So on the x-axis of this plot over here, you've got the scan location, goes from about 1 to 7, and that corresponds to values of, 0 to 7. So that corresponds to values of 0 up to 7, which is about the value of delta nu on this Echelle diagram. And so what you'll see is that a value of about 2 gives you a pretty low performance value. So you're trying to minimize that performance value. Values of around 2 are pretty good. And that makes sense because in this Echelle diagram over here, you see there's a bunch of peaks at x equals 2. And then again, you get to a pretty low value of about x equals 5.5. And so if you come back to the Echelle diagram, you see there are 4 peaks that fall in a vertical line where x is about 5.5. So that's how it works. So in addition to those 3 measurables, the residual sum of squares, the gradient, and the line length, Will also added a measure of gaps in the line. So basically how complete is that straight line? And he also included the autocorrelation, because as I said, we know it works. And when he combines these features together, he's able to pick out the bad stars that have no patterns and the good stars, which have nice patterns. So he also needs a sample to work on. So here's an HR diagram of all ANF stars that were observed at 2-minute cadence by TESS. You'll notice that there is an overabundance near the zero age main sequence. So there's an overabundance of stars down here compared to, slightly more evolved stars. And that's actually a selection bias. Once we realized that these high frequency delta Scuti stars were preferentially young, then we specifically targeted them for TESS observations. So Will started off with nearly 300,000 TESS stars. He made a cut on this temperature range, and that left him with about 45,000 ANF stars to look at. But not all of those stars are pulsating. He had to work out which ones were pulsating and which ones weren't. In 2019, I realized that a good way of determining whether a star is pulsating or not, if you want to boil it down to a single number, is you take the Fourier transform of the stellar light curve and you just calculate the skewness of the amplitudes. If the light curve is just white noise, you'll have a skewness of 0. If it's got various noise, like if you've got red noise, a lot of instrumental noise going on, you'll end up with a fairly low skewness. And if you end up with strong pulsations, you'll have high skewness, right? Because your Fourier transform is just going to be going up and down with all of the peaks from the pulsation. And so you can see in this diagram, this is signal to noise on the x-axis and skewness on the y-axis, both in log form. There's a population of pulsators. Then there's a sort of rarefied gap, which is, I guess, stars that have either pulsations that are very low signal to noise, or there might be peaks that come from other sources. You might have some instrumental noise or something. And then there's a whole population of non-pulsators. And so somewhere you can draw a line that's going to divide pulsators into non-pulsators fairly well. And the threshold that Will used was 0.3 in log skewness. That gives him about 9,200 pulsators to work on. I'll also mention Nick Barbara at this point. Nick has led a paper using lots of different statistics, not just simple things like skewness and signal to noise, but a whole bunch of stuff to do this in a more robust way. And that's a paper that's, I don't remember if we submitted that or if it's in review at the moment or if it's about to be submitted, but yeah, that's another undergraduate project led by Nick. So Will took these 9,241 pulsators. He did his machine learning magic, which consists of the 5 features, and he also manually confirmed the results. He ends up with 340 delta Scuti stars with regular frequency spacings identified, right? So these stars with those nice regular patterns. And that allows us to do these population statistics. So, as I mentioned before, there are more stars near the zero-age main sequence. That does suggest it's the younger stars only that have the regular patterns, but there is a selection bias that we're very aware of. What's also apparent is a gradient in delta nu. So this is color-coded in this diagram. You'll notice that towards the lower left of the diagram, there are many more stars that are sort of a yellowy green color. And then as you go towards older stars, which are going to have larger radii and lower densities, then the fill color becomes sort of bluer, so values closer to 5. The points in red are the 60 stars that were included in the Nature paper led by Tim Betting. Okay, so the fact that there is a gradient suggests that the denser stars have higher delta nu, as we suspected, and that as stars evolve, they get less dense, hence we observe the smaller delta nu. So everything is as we expected. A better way to look at this is with a histogram. There's lots of information in this histogram of delta nu, right? So again, we've separated out the Betting et al. Sample, and then in blue, we've got all the extra stars observed by Will. For reference, Pleiades stars, the ones I showed earlier, all had delta nu between 6.7 and 7.0. Now, the fraction of stars with discernible patterns goes down as stars evolve. And that's just something we've noticed. If we go to our HR diagram, we don't see many evolved stars, and we know that they will have lower delta nu. So that readily explains why there are fewer stars towards the left of this histogram. Conversely, very high densities are needed for a delta nu of 8.0, okay? This requires very low metallicity, and it requires the star to have a truly sort of zero-age main sequence, age where the star is at its densest. Even then, if the star is rapidly rotating, it will become oblate. That gives it a lower density, and that shifts it to the left in this diagram. So that explains why there are fewer stars at high values of delta nu around 8.0. Now, there are many stars at delta nu of around 7. This is because this value is achievable with a wide range of metallicity and mass. It also includes rotators that would have been over to the right, but have been shifted to the left. And it allows for some evolution before or after the zero-age main sequence. Your star doesn't have to be exactly on the zero-age main sequence to get a delta nu of around 7. The fact that there are so many stars in that one bin might suggest there is some methodological bias. So if, for instance, if Will's training sample had more stars that had delta nu near 7, then there's possible bias there. And we haven't explored that because Will ran out of time for his project. But as I say, this was an undergraduate project. I'm very proud of the work that Will achieved. Okay, this is my last science slide now. I just want to come back to the Pleiades one more time. The observations that I showed earlier were all from K2, but TESS has also observed the Pleiades now. This is a figure that Tim Bedding made. The x-axis is BP minus RP color, so it's B minus R color. So effective temperatures here are roughly 6,500 Kelvin at the far right and maybe 10,000 Kelvin at the far left. And it's just a color magnitude diagram, but what it shows is there are many high frequency delta Scuti stars in the Pleiades, not just the 5 that were observed by K2. And you can see that they all fall on a sequence as you would expect for a stellar cluster. So this is very clearly the zero age main sequence, well, not zero age main sequence, sorry. It's the main sequence at some age, maybe about 100 mega years. But there are some stars that don't fall on the sequence. So for instance, this particular star over here, maybe that's over here because it's reddened. So it could have been in the pack over here, but reddening has pushed it over to the right. And then there are some stars that clearly just lie above the rest of the pack. So these could be binaries, which give them a higher luminosity if they are interpreted as a single star. Or maybe this is a rotator seen polon, which has pushed its brightness up. So we've got heaps more work to do with these stars. I'm confident we're going to get some very tight constraints on the cluster age in the end, and that will also necessarily include rotating models. Okay, so here's my summary. Mode identification is now tractable for young intermediate mass stars. Asteroseismic ages for young stars can recalibrate stellar ages. So given that cluster ages are usually determined relative to each other, this means we can improve the entire system for stellar ages if we can improve our benchmarks. I talked a lot about HD 139614. This is a young star with a planet-forming disk. It's still on the pre-main sequence, and we get an age with only 7% uncertainty, which is really good. There's lots of work to be done with these protoplanetary disk hosts, including the spin orbit misalignment that I mentioned as a project. The Pleiades, I think, are a really exciting, quote unquote, new target because this is the first time we've had these amazing data. And then last of all, rotation is both very important and very troublesome. I'm going to be doing my best to model rotation. It's not straightforward, but with asteroseismology, we can measure the internal rotation, and that is really going to change the way that we model these stars. That's it from me. Thanks very much for listening.
Okay, thank you, Simon. Are there any questions? If you do, please raise your hand or ask away.
I have one.
Hi, Simon. Great talk. So I just had a question because rotation is very difficult and it's something I'm dealing with right now. Your delta Scutis are rotating quite quickly because they're quite young, and it's changing the density profile of your models. Generally speaking, asteroseismic rotational measures, so measuring the rotation using the rotational splittings, assumes that your model is non-rotating. So how are you reconciling that with your work?
So I will be calculating rotating models using MESA. There are various options that go into this. For instance, do you want to have a star that's uniformly rotating, or do you want the core to be rotating more quickly than the surface? We have some observations of older pulsating stars where we can measure both the core and the surface rotation, and stars do seem to be uniformly rotating towards the end of their main sequence lives. We don't have good constraints for that for younger stars. But for now, partly for the purpose of simplicity, I create models that are uniformly rotating. And so we can therefore include the structural effects of rotation as well as those frequency splittings that we get in the way that rotation affects the pulsation modes. Does that answer your question?
Yeah, thank you.
Cool. And the rotation rates that we see, they do span quite a wide range, right? So the stars in the Pleiades, if I pull those back up, We've got V sin I of 10 for the slowest rotator. We've got V sin I of 100 for the most rapid of these three. And then there were 2 other stars in the sample that had V sin I over 200. So there is a wide range. And one option is to focus on the slowly rotating ones where, if you get the rotation wrong a little bit, it's going to be less important. Like it's going to, be a smaller error, basically. I think there might have been a question in the chat.
Yes, so there's a question in the chat. I mean, I can read it out, or maybe, yeah.
Yeah, I'll go for it. Alexander Kemp is asking, I mentioned early on that eclipsing binaries are systems that can help constrain modeling uncertainty. I was wondering if you could elaborate a little on what these systems in particular offer. Yeah, so eclipsing binaries give you fundamental stellar parameters pretty much from geometry alone. Like if you have a parallax and you measure eclipses, you get a lot of stellar parameters just from geometry without having to rely on stellar models. And then if you also have a way of measuring dynamical masses, whether that's from radial velocities or from pulsation timing or something, then you can get masses, radii, temperatures, luminosities, all of these things without actually having to resort to stellar models in any way, right? And so that gives you really tight constraints that you then have to match when you're trying to compare your pulsation frequencies to stellar models. And so I might construct a whole bunch of stellar models where I've assumed some value for overshooting, and then I might realize later for an eclipsing binary that the only way that I can get the pulsator in an eclipsing binary to fit both the models and the eclipse constraints is to change that overshooting parameter by some value. And so it's in this way that we start to improve the physics, or at least constrain the range of the parameters that go into our stellar models. And these are parameters that are otherwise close to impossible to determine, right? You can't just look at the convective core and determine how much overshooting is going on. So that's why eclipsing binaries are particularly important.
Okay, thanks. I guess I have a simple question. Maybe I missed that. What exactly is the origin of the pulsations? Because is it some kind of internal processes in the stars, like convection or something else, or is it could be coming from a binary companion or some accretion from the disk or something like that?
Yeah, so I didn't explain that. For these delta Scuti stars, it's a heat engine mechanism. So you get a layer of the star that heats up upon compression and then later on releases that energy. And so the star's just sort of getting bigger and smaller over time. And as it does so, it's getting brighter or fainter. So that's one way you can drive pulsation. In stars like the sun, where you have large convective envelopes, it's a stochastic process. So, stars are basically noisy environments with a lot of convection and stuff going on. That causes the star to oscillate at its natural frequencies. And there are more processes that can drive pulsation in different types of stars. But as far as the stars I mentioned, those are the 2 most important ones.
Okay. I have some follow-up questions, but I think I'll let other people to ask. I think Daniel Price has his hand raised first.
Simon, I was just wondering, so if I understood you right, then you're basically measuring the density. Is that a fair statement, or are you doing something more clever with these other mode identifications than just getting density?
Yeah, to be specific, what we're doing is we're taking all of the models that we calculate, so every evolutionary track sampled at many ages, and we're saying, what are the pulsation frequencies for this particular model at this particular age? And then we're comparing those very specific frequencies that we get out of the models with the ones that we observe, and we're looking to minimize the differences. So that's what I meant by that chi-square minimization. So it's a bit more than just trying to match the density, but ultimately, yeah, it's the density that's the parameter that determines what the pulsation frequencies are going to be. There are some more complications beyond that. For instance, as a star evolves, it gets more centrally condensed. So you actually end up with an internal density profile rather than just a singular value for the stellar density. And so that matters. And then also over time.
Constrainable?
Sorry?
Is that constrainable?
It certainly is. Yeah. If you get enough of these pulsation modes, and if you've got tight enough constraints for, I don't know, let's say, you had one of these eclipsing systems where you've got well-measured mass and radius or something like that. Yeah, you can really start to look at the internal density profile. Another thing you could look at is whether the rotation profile is truly uniform or whether there is some internal differential rotation. So if the near core region is rotating faster than the surface or something like that, those are things that you can in principle do. We're not quite at that stage yet. As I say, my first task is to do is to fit the Pleiades stars with proper rotating models. But yeah, in principle, in the long run, that's something we can do.
Thanks.
Okay, I think last question by Simon Campbell.
Hi, Simon.
Okay.
I had a corner plot where we explored the model parameters. And just wondering if overshoot was in there. I saw MLT, there was no dependence.
Yeah, so we just assumed some value of overshoot in this particular case. No, we didn't vary the overshoot. Yeah, we just used the mixing length for this one. Because the star is so young, I don't expect overshoot to be particularly important because, the core is basically full of fresh nuclear fuel already. So whether you're getting overshooting from the convective core and pulling in fresh hydrogen, basically not important at this age. If I was modeling a star near the terminal age main sequence, that would be very important. And so overshooting is a parameter I would definitely want to vary. But yeah, for simplicity at this point, we didn't model overshoot.
Okay, thanks. Nice talk.
Thank you. And one of the other things I was going to mention in response to Daniel's question is that as stars evolve, the G mode cavity, which are modes that are driven in the near core region, that cavity starts to overlap with these P modes, which are the modes that I've been talking about this entire time. So they're basically most sensitive to the surface regions of the star. And so as those cavities overlap, the frequencies can interact and sort of get shifted around. And so old stars are actually much more difficult to model in that sense. So there's quite a few things going for these young stars. They're basically homogeneous. The P and G mode cavities are well separated. You don't have to worry about parameters like the mixing length and the overshoot quite so much. And that's another reason that we are so optimistic for doing well at measuring the ages of these young stars near the pre-main sequence or on the pre-main sequence.
All right, thank you, Simon. I think we've passed the hour, so it's a good time to stop the recording. And thanks, Simon, again for his talk.
Thanks for having me. Thanks.